For most of the signal chain, the audio signal is electricity. And while you don't have to be an engineer to hook up an audio system, a basic grasp of electrical theory is necessary to understand audio terminology and interfacing practices. It's also invaluable for troubleshooting. This lesson is a primer for those who have no electronics background, or who do and have not worked with audio systems. Fortunately, the principles of operation of electrical circuits are similar to those at work in the fluid and mechanical systems that we use every day. As one audio sage put it, you know this stuff, you may just not know that you know it. Nature loves equilibrium. Whenever it does not exist, nature will exert forces to bring it about. This is why the wind blows and why rivers flow. It's why a pin rolls off of an uneven tabletop. It's why water pools in a low spot on the floor. It's why a hot drink or a cold drink eventually become room temperature. Stated another way, nature loves balance, and it will seek to correct an imbalance. This scale shows the establishment of mechanical balance. The equal sign in an equation is the mathematical equivalent. Humans have learned to harness nature's insistence on balance to accomplish some useful tasks. Waterfalls and windmills are notable examples. In both cases, nature is flowing something to correct an imbalance, a process that could be called equalization. We can convert the hydraulic or pneumatic energy into another useful form, such as the electricity that ultimately powers our audio system. Power is the rate at which energy is converted, or the rate at which work is done. For example, if the water level becomes equal, the flow stops. If the air pressure becomes equal, the wind stops. If the imbalance persists, then we have a continuous power source. Since electricity is invisible, the concepts are not intuitive. Fortunately, the principles at work in hydraulic and pneumatic power delivery systems are also at work in electrical circuits. These analogous systems are easier to understand. Here are a few examples. An aerosol can has higher internal than external pressure. When the two are connected, nature equalizes the pressure difference by flowing air. The rate of flow of air is the current, and the flow can be maintained for a period of time before the source is depleted. And that occurs when the pressure inside and outside of the can is the same. A mechanical power source may be a compressed spring. The imbalance created by winding the spring can be a power source for moving the hands on the clock. A child's toy may use a stretched rubber band as an engine. When the energy stored by the stretching is depleted, the plane falls to the ground. Squeezing a tube of toothpaste makes the internal pressure higher than the external pressure. The toothpaste flows to equalize the pressure difference. While nature causes the flow to take place, it also opposes it. Anytime we try to move or flow something from point A to point B, whether it be fluid, air, an object, or electrons, there is a force that fights back. The umbrella term for this opposition is impedance. A mechanical impedance is opposition to movement. Electrical impedance is the opposition to the flow of current. Acoustic impedance is the opposition to the flow of air vibrations. Impedance comes in two forms, resistance and reactance. A resistive impedance dissipates the applied power in the form of heat. Friction is a mechanical example. A reactive impedance stores energy and reflects it back to the source. Mechanical examples include a compressed spring or a moving mass. In both examples, energy storage is taking place because the impedance is reactive. If you blow through a soda straw, your lungs, the power source, encounter resistance since the airflow is restrained by the straw. A smaller straw produces more resistance, and therefore less flow and higher pressure. A larger straw produces less resistance, and therefore more flow and lower pressure. The straws produce a resistive load to your lungs. The same effort may be expended to inflate a balloon, but in this case some of the applied energy is stored. If the balloon neck is not choked off prior to the next breath, the stored energy will reflect back to your lungs. The balloon is a reactive load. Impedance includes both resistance and reactance. Like mechanical loads, electrical loads may be resistive, reactive, or both. Audio examples include loudspeakers and transformers. The impedance equation allows a load to be analyzed mathematically and plotted for analysis. This was introduced in the time domain lesson. In words, the equation says this: locate the resistive value of the impedance on the x-axis and the reactive value of the impedance on the y-axis. The total impedance is found by determining the distance from the origin on the plot. While that's a more in-depth analysis than we use for day-to-day audio work, it's presented here as an introduction.